Well, welcome back, everyone. Today, I'm honored to be joined by Frank Cheng. Thank you thank you for joining me.
You're welcome.
Yeah.
hmm
So we'll jump right in. You've done quite a bit of research with graphitic material. So, what is graphitic material, and where does it come from?
Well, it occurs naturally, but it also can occur synthetically. Good quality graphite is a crystal, and the crystalline plane is a two-dimensional plane, resembles chicken wire, and the chicken wire
Interesting.
lattices stack on each other. Um, Now, when it occurs, it is a material that's it's a mineral also, mined for primarily lithium-ion batteries.
Okay.
Uh, and the synthetic stuff, and I work on a synthetic graphitic material. I would say a cousin to it.
Yeah.
Yeah, yeah.
And so, what about it makes it a good um, material for using it in batteries?
Graphite itself, because it's a two-dimensional stack, and the between the graphitic planes, it's called graphene. Each plane is called graphene. Allows intercalation of ions. And so for lithium-ion battery, it'd be the lithium ion.
Got it.
And then that's how charge is stored in the battery.
Okay.
Okay.
And you work with synthetic graphene,
Yeah,
graphite.
I work with this cousin, and it's not very good graphite. Is what it has some characteristics that are similar, but it has more structural defects in each graphene plane. We discovered this by accident. Oh, maybe 2009 is where I think it began.
Okay. And were you the original discoverer of this material?
Yeah, I was probably the first to describe it.
Got
Now,
it.
we look through literature. I had my grad students. Keep looking, even now. There are probably instances where it appeared, but people looked at it and probably just dropped it.
Yeah.
Yeah.
And so why are you working with a synthetic as opposed to like actual
Well,
graphite?
in this case, I'm looking at it specifically as an electrode material, and it has better characteristics than graphene or graphite as an electrode.
What makes that the case? Is it just
Okay, we didn't understand that in the beginning. There was a couple of reasons why. I would say there was a reason that had to do with uh, electronic states. And this is the ability for electrons to hop from the surface of an electrode into something in solution. Okay.
okay?
Okay. If you have a low density of these electronic states, the hypothesis is that that you have a poor electrode material, and that's what people are hypothesizing in the beginning for graphite and graphene. Now, this is off the basal plane, off the flat plane into solution, and that's what we believed in the beginning. I
Okay.
looked up some. I looked up some computational papers, and in these papers they did describe the increase in density of electronic states if you have more structural defects. And I went with
Okay.
that hypothesis for a long time.
Yeah.
The past 5 years, I've really changed my mind.
Okay.
Okay, what happens is, and seems obvious now. Well, you know, carbon, especially graphite, it loves to absorb organic contaminants, and that's why we use charcoal filters in water.
Got it.
It
Yeah.
just absorbs right. And there was an interesting paper that came out about 2012 in a major Journal of American Chemical Society, and I read it and I didn't believe it. Okay, and they said, well, we see that when you have a fresh graphene plane on graphite, and graphite is very interesting. You can look it up on YouTube. You can get a new graphene plane if you just use Scotch tape and peel it off. And then you got
Okay.
yeah,
Yeah.
right. Well, they were claiming, well, you have fast electron transfer. Okay,
Right.
right. And I said, I don't believe that. So we put it aside for a while, and we tried it a few years later with just our graphite samples, and it worked. I said, well, why hadn't anybody ever seen this before besides this first person? And then he has a series of publications based on that. And then he didn't have an explanation for a while. So we found an explanation from a Korean group a few years later, and their explanation was very simple. Graphite and graphenes love to absorb contaminants, organic contaminants.
Similar to charcoal.
Yeah,
or coal.
yeah, just charcoal, right? They're called volatile organic compounds, and they can emanate. Humans emanate volatile organic compounds. Carpeting does, clothing does. So it's just everywhere in an indoor lab setting. And so what made our material less likely? It's a better electrode. We observe faster electron transfer. What made our electrode material better? Well, because it has these structural defects, it's not as efficient at absorbing these volatile organic compounds.
Yep.
Okay, so that was a simple reason why it has fast electron transfer, and why we see it's a better electrode than graphene or graphite.
Got it. Because of its defects. Its
the defects, structural. It's less efficient at absorbing volatile organic compounds.
Got it. And so therefore, the problem with graphene and graphite is if they're too perfect, the electrons have a difficult time moving across them. Is that?
Yeah. Well, the volatile organic carbons foul the surface. It presents a resistive layer, a barrier to like. Yeah.
So that imperfection means that there's less that attaches to it.
Yeah.
And so then it becomes easier for the electrons to move across
exactly.
it.
Yeah.
Got it.
So now, given that hypothesis, we kept moving forward. Said, well, can we decrease the amount of absorption on the surface? And the answer is we did. We just introduced lots of, they're called functional groups, oxygen functional groups, and it makes the surface very hydrophilic, water-loving. We have a paper on super hydrophilic characteristics. And there we see that it's indefinitely stable as an electrode.
Meaning?
That could just, there's fast electron transfer over days and weeks of using this material. Okay. Now that's important for sensors. And so we're looking at sensor work lately for this material.
Right.
One of which you mentioned earlier is dopamine. We're looking at it as a dopamine sensor, for instance.
Interesting.
Yeah.
So how would it be a dopamine sensor?
Dopamine has electron transfer characteristics with electrodes. And for graphitic materials, graphitic materials probably have a lot of ideal characteristics, one of which is they're inexpensive relative to other materials.
Right.
And the problem is they foul. There's absorption of unwanted materials on the surface. Well, we can avoid this adsorption with our super hydrophilic sensor, with the pseudo graphite, we call it.
Got it.
Okay. Now, we have an acronym for it. It's called Graphite from the University of Idaho Thermalized Asphalt Reaction, and it's guitar.
Guitar.
Yeah, but I call it pseudo graphite too.
There we go.
Yeah.
Okay. And the reason that making it hydrophilic will help it in the long term is because the water will take all of the variable organic compounds and not the graphitic material. Right. Water will be preferentially adsorbed to the surface in place of the organic compounds that would absorb onto the surface of this material. Got it.
Yes, right.
And when you talk about electrons moving across it, what do you mean by that?
Well, the electrons, you create a driving force for the electrons to move from the electrode into an acceptor in solution, or vice versa. You can do it the other way, move it back and forth. And you can create a driving force. Now, there could be a barrier to that driving force. And a barrier would be, a logical one would be a resistive barrier at the surface.
Right.
And that would be the volatile organic compounds.
Got it. Okay. And because electrons move across the surface.
Yes.
And so if there's any debris, as it were, it makes it travel more difficult.
A barrier, yeah, right.
Got it.
And the fancy terminology is heterogeneous electron transfer. Okay, you're going from a solid into something dissolved in a solution or liquid state.
Okay. Yeah. And that solution is generally water, correct?
Could be organic solvents.
Okay.
Yeah, lithium-ion batteries require organic solvents.
What is in that lithium solvent? Or
it's an organic solvent. There's several ones that are commercially used. The reason you can't use water is that the driving force to move the electron, excuse me, in this case it'd be the lithium ion back and forth into the graphite electrode and out, would break water down, okay, into hydrogen and oxygen.
Got it.
And yeah, that'd be an explosion.
Is that because of its power or just because of its nature?
The driving force required.
Got it.
To move it. Water has, it's called a potential window, has a potential window of about 1.2 volts. Well, you know, lithium ion batteries have about 3 volts of driving force and also to charge it up. That would just break water down. And that's why
got it. So
organic solvents are required.
Right. And that organic solvent is not water, it's generally
well, could be something simple. The ones we use it's called acetonitrile, and pretty simple. I mean, methanol would be a possibility. I don't think methanol is used in lithium-ion batteries. And alcohol of some sort. Other ones are propylene carbonate. These are just all simple organic solvents.
Right.
Okay, yeah.
So does the lattice structure of it, the chicken wire structure, as you mentioned before, does that, how does it influence the movement of electrons across it? Does it help them, or is that more of a hindrance?
Well, the chicken wire lattice would be provide the electrical conductivity that you can move the electrons through the material into solution. And so if you look at graphite, the base plane of the chicken wire lattice is called the basal plane for obvious reason.
Right.
If you look at the edges between the chicken wire, you can cut it down there, and that's called the edge plane. And so the lithium ions seep in through the edge plane between the graphene planes, which are the chicken wire lattice.
Got it.
Okay. And then it goes deeper and deeper. That also presents kinetics, or the time it requires to charge.
Got it. So it's less like a road and more like a one of those maglev trains in Japan, where it's kind of like there's barriers on both sides and it just goes down the middle. Is that right? Or
yeah, it goes through. It goes through between the planes of the chicken wire, right?
Got it.
The lithium ion in this
case.
Yes.
Yeah. Okay. So when you're making this, well, how do you go about making this guitar substance?
Oh, well, that's interesting. It was an accidental discovery. I had a former graduate student, and he had this oil shale from Colorado, and there's a third of the world's petroleum reserves are locked up in this shale, and it's just too tightly bound to be commercially available. So there's lots of interest in looking for other economically viable components in this shale to make it more viable. And he thought this shale had rhodium in it. I said, well, that's a precious metal. I said, I'm going to really doubt that. But I said, we have this apparatus called a flame atomic absorption spectrometer. And you put it through a flame and you watch for signatures for the particular element. Said, well, I looked at it and I said, well, his name was Jeremy. Jeremy, I think you're going to probably have to burn off all that carbon first before you put it through. It would obscure everything in that flame to see this. So he would burn it off, and we'd see a residue, and the residue would look very metallic. And that was guitar. And I picked at it and said, well, that can't be rhodium. That's what I looked at. So I picked at it, and it was layered like graphite.
Yeah.
And I said, that's a form of carbon. And that's where it began. So lately, what we do now is we don't use that apparatus. We used it for years. What we do now is inject a spray of. Okay, I have a colleague in engineering. They use diesel. I use vegetable oil in my lab. There's no storage restrictions on vegetable oil. Okay.
Yep.
So I use vegetable oil in my lab. We just go to the local grocery store and pick up a few gallons. Usually we get weird looks when we do that, by the way, okay? But we pick up a few gallons and we spray it into a hot, it's called a tube furnace. It's a tube along with nitrogen gas. And we have we call it target. We put our, could be a piece of quartz or could be particles, and we coat these, our guitar onto these particles or quartz. And it's at 900 degrees Celsius.
Okay, so it's pretty hot.
It's pretty hot. It's at 1600 Fahrenheit, something like that. Yeah, right. Okay.
Hotter than we could survive.
Oh, yeah, absolutely.
Yeah.
Yeah, so we coated on titanium, quartz, silicon wafer chips onto basically sand, diatomites. We coated on iron particles. And the iron particles are very interesting, by the way. They're magnetically susceptible, so we use that.
Right.
Lately, what we're doing there with the iron particles, I published this last year, is we take guitar, coat the iron particles, and we've learned to attach DNA to these iron.
Oh, fascinating.
Yeah. The single-strand DNA. It's the half the DNA, double-strand, right? And then we look for a particular target in solution, and we can pick up these target strands. We can look for specific sequences of DNA. And now we can electrochemically detect these things, or we could use a polymerase chain reaction and amplify the target sequence. And what we have going on is that's been a challenge. It's called polymerase chain reaction. It takes about 8 hours to completely do, because there's a few separation steps that take a long time. But with the magnetically susceptible iron particles, we could pull it out of the sample solution very quickly. We could also pull it out of the PCR solution.
Right.
And we can forego those separation steps, and we can do PCR less than 2 hours. So we quadruple the rate of PCR.
Right.
And I have a student demonstrating that now. And
okay.
But for detection purposes now, using PCR and detection methods, we're using what's called visible spectroscopy in that paper, and that's changes in light optical density of our material. We have pretty low detection limits. With electrochemical techniques, we can skip the PCR steps, so we can do it in 10 minutes. And we have detection limits this is preliminary data, but are the lowest we can locate in literature. Okay.
Wow.
So so we're working on those. But
right.
Okay, so I'm really moving you astray here from.
No, this is fantastic.
Okay.
This is awesome.
Okay.
So the polymerase chain reaction.
Yeah.
How does that process work?
Well, it's based on an enzyme, and it's famous because it's you see in the detective shows, right? They'll talk about doing PCR in crime scenes.
Okay.
And the big gripe is, this will take a day or two, and it does. It takes a day or two. You have to get priority. So we hope to speed up the forensic possibilities there.
Right.
Okay.
And when you're doing that process, what are you looking for?
Well, we have a DNA sequence, each of us, that are unique to the individual.
Right.
There are certain sequences that are. There's a lot of commonality also.
Yeah.
But we're looking for for pathogen detection, we've looked at salmonella sequences. Okay.
Got it.
Right. And so the first publication we put out last year was based on looking for salmonella sequences in basically raw chicken soup. Okay. So,
got it.
Okay. We didn't see any, but we did spike in these sequences to make sure that we could pick it out of this raw chicken.
Right.
Raw chicken soup. Essentially, we squeeze the chicken here.
Fascinating.
Right. I have to be careful because I don't have a biosafety license in my lab here.
Yes.
Okay.
There you go.
Okay.
So when you're performing these tests, why are you bonding the single helix of DNA onto graphite or this?
Oh, because
guitar?
this particular sequence is going to be unique to picking up the target sequence
What do you mean target sequence?
The target sequence is that unique set of sequence of DNA that could point to a particular pathogen like salmonella.
Got it. Okay.
Could be COVID, could be a variety of things.
Right. So it's like it's barcode.
Yes, it is. It is. Right.
That's
a good analogy.
Okay.
Right.
So you're looking for that. You're looking for the salmonella's barcode.
Yeah.
Why do you bond the DNA to graphite? What does that enable that bonding it to something else wouldn't?
In this case, it's graphite on the iron particles. That way we can put this graphite on iron particles with the right DNA sequence in the sample solution, then pull out if that target sequence is in the sample solution, pull it out of the sample. Okay. Now that allows you to do two things. We can do an electrochemical analysis right after that, which wouldn't be possible in a sample solution, by the way.
Right.
Okay. So that's the purpose there. And the other one is to do our own kind of take on PCR, which we can do 4 times faster now than standard techniques.
What enables you to be able to do it 4 times faster?
Okay, we skip because we have this magnetic particle with the right DNA sequence on it. We pull it out of solution. We put it in a solution that allows us to do PCR, and it's an enzyme, an enzymatic process. And now the PCR solution, though, in traditional PCR requires a separation technique called electrophoresis. And that takes a little while and some operator experience. But in our case, we could just pull it right out again with a magnet.
Got it. Yeah. Is that because it's attached to the graphene,
the graphite,
to guitar?
Yeah, the guitar on top of the iron particle.
Got it. Yeah. And so you can pull out the DNA enzyme.
The DNA target sequence that's been amplified. Okay.
That's been amplified, meaning you made more of it, correct?
More of it, right. Yeah.
So you can pull that out by the fact that it is attached to the graphene, which is attached to the iron.
Then we could separate it out in another solution. Yeah, it's called denaturation. It requires heating up to 90 degrees.
Okay.
Yeah. I mean, people have tried this before, but the DNA to the surface bond has been weaker on their approach. Ours is much stronger because it's a carbon-carbon bond.
Okay, that's what makes it so special is the carbon-carbon bond. Yeah.
Previous attempts have been with a gold-sulfur bond, and that's much, much weaker, and it won't hold up to PCR, which requires heating to about 95 degrees. So the thermocycle goes up to 95 room temperature up and down.
Got it.
Okay, yeah. So
fascinating. Okay, right. So why only use a single helix of DNA?
Oh, because you want to form the complete duplex with the target. The duplex is a double strand.
Okay. Yes.
Okay.
Yeah.
So the target is another single strand in the sample solution. So we've tried to see if we can contaminate the process by using false targets with mismatched pairs, and it won't work.
It won't work.
Yeah.
Got it. Yeah. So you take the DNA, you just take one helix that has the salmonella, for example.
Yeah, complementary sequence to the salmonella target.
Right.
Yeah.
And then you try and match it to this other sequence, which is attached to the guitar.
Yes.
And if it doesn't match up, there's no salmonella in this, whatever it is.
Right. Yeah.
Got it.
Yeah.
Fascinating.
Yeah, right.
That's wild.
Yeah, it's DNA. I'm learning DNA myself. I've always had, as a chemist, I've always had interest in it, and it's the nice thing about academia is that I could stop and look at this whole new chemistry, and basically, I mean, I would say I have an undergraduate knowledge of biochemistry, but it's getting up there. But it allows me to sit back and just read on my own. Just get old textbooks and surf the internet.
Yeah.
And right.
As far as graphite and as well as guitar, is there anything that makes it different from from other carbon-based materials?
Yeah, it's the extreme defects of that are in guitar. And you know, when I got it, again, this gets back to why I got in academia. I started looking at graphite. Initially thought when I saw the experiment coming out of it was called pyrolysis of oil shale. It looked metallic, and I said, I think it's a type of really crystalline graphite, and I thought it was graphite, and hence we were calling it graphene initially, because that was the term to use, you know, to get funding back then.
Yep.
What I learned in general chemistry was the graphene plane was that chicken wire lattice fence.
Yep.
And, I thought it extended forever. Right. It doesn't.
It doesn't.
No. Okay. Then I have to step up maybe to like a third year material science knowledge background, and they're crystallite. They're crystallites in these planes, and they only extend so far.
Right.
Maybe a few microns. Right.
Interesting.
Okay. And then they terminate. You have defects, and then you pick up on another crystallite plane. Okay.
Got it.
Okay, so it doesn't extend out forever.
Right.
Good quality graphene, by the way, may go for a few millimeters. Okay, but that's
really
yeah. But in our material guitar, those crystallite platelets are maybe a few nanometers. It's really defective.
Really tiny.
It's really defective, and so we don't have an atomic force microscope on this campus, but I couldn't understand this until I saw it's called AFM, an AFM micrograph of our material. So on a good quality graphite, it's highly oriented pyrolytic graphite, HOPG. It's basically flat.
Right.
Okay, what atomic force microscopy does, it's like a phonograph needle, and it'll bounce up and down on the surface. But so you could see how flat your surface is, down to the atomic level.
Right.
So I had two samples, and there was a trade show going on at the scientific conference in San Diego, and I brought it down to these guys. I said, "Can you run these for me real quick?" And one of them was HOPG, atomically flat, and the other one was this guitar, and you could see a highly modeled surface. It had it looked like a series of surface bubbles going up and down.
Fascinating.
And so that's where I understood this material is not. It's low quality graphite, essentially, is what it is.
Right, because it's not. It's more like a mountain.
Right.
A series of
it goes up and down.
Landscape.
Yeah, right. It's very
Got
very
it.
wavy surface. And a couple of things that allowed us to do is now we understand. I had a tip off from a former not a graduate student, but an undergrad here, but he got his graduate degree. We're a Nobel Prize winner, by the way.
Wow.
For fullerenes.
Fascinating.
Yeah, but
Congratulations.
For my former student.
Yeah.
He worked there at Rice University. But he got back to me once and he said, you can do chemical modifications on the surface. So I started learning about chemical modifications, and it turns out they're preferential for these defects, and that's why our material is so good at you can't modify graphite with their single strand DNA, but we can do it with guitar.
Got it.
It's the defects that make it chemically give it the chemical modifiability. Yeah.
Why is that the defects
the why
are so
is that?
for?
Because a crystal is a very stable structure, and so you have to break up the stability first
in order to introduce something new.
Yes, right.
Got it.
Now when you have a defect, it just wants to react.
Right. It's unstable, so it's
unstable.
Interested in something else.
Yes, right. So
Got it.
One of the things we can do is attach. Well, we're doing other things now, but we can attach. The big one's DNA. Okay.
Yeah. Got it. Yeah. Okay. So this graphitic, the pure graphene with that's kind of micrometers, perfect.
Yeah.
Is it similar to I don't know if you've seen these videos of snowflakes forming on a bubble?
Yeah.
Where they kind of overlap and crush each other.
Mm-hmm. That could be a good analogy. I scraped the ice off my windshield and I could see crystallite planes of I think this is the same analogy of ice on my windshield.
Right.
And you could see it go out, extend, and see another crystallite plane come out.
That it kind of overlaps with
yeah,
crunches into. And that's what makes it imperfect. Is that more or less correct, that there are a bunch of different graphite structures that are perfect and then they keep running into each other and that creates the imperfections?
Yeah. That would apply both to guitar and just graphite.
Right.
Yeah.
Okay.
Yeah.
Got it.
It's just our material's got a lot more defects.
A lot more defects, which makes it needy, as it were.
You could put it that way.
Yeah. So graphene how is graphene different from graphite?
Oh, graphene is just one plane, one chicken wire type of fence plane of material. Yeah.
Got it. So it's so it's not really that it's not just a smaller. It's just less.
And again, you can look this up on YouTube. People isolate graphene planes with Scotch tape that keep pulling down until you get to a single plane.
Yeah.
Yeah.
There are a lot of people excited about graphene as like the new super material.
Yeah, I can't remark too much. I know graphene more as an electrode material, and I'd say it's limited. Okay. Now, in terms of other applications, I'd say there's probably a lot of possibilities. It has very interesting mechanical properties. Okay.
Interesting. What do you mean?
It's very strong for being basically a one atomic level thick material.
Right.
Okay. So I imagine there'd be material applications. Again, you'd have to, I'm going way out of my expertise on this. You'd have to talk to material scientists on this.
Okay. Interesting.
But in terms of electrode material, there have been a few publications indicating that it's been somewhat disappointing.
Got it. Yeah.
Some of that disappointment comes from its relatively slow electron transfer, which I believe is not electronic, but it's just the absorption of volatile organic carbons.
Got it.
Yeah.
Okay, so it's too perfect, and so
it loves things. Yeah, it loves to attach. Yeah, it picks up. It's an absorbate. It absorbs all sorts of things from the atmosphere.
There you go. Okay, so as far as its potentials in batteries and such, would you see that as limited?
Yeah, I would say so, and then watch someone
prove you wrong. Yeah.
All right. So, there's this application. It's a cousin to battery called ultracapacitor, which is it's not a battery because all it's doing is absorbing ions into each surface, and there's no change in what's called oxidation states.
Right.
Okay. On either the cathode or the anode, positive or negative electrode, and there's a lot of hope there, and I imagine you might see a few applications there with graphene. I haven't kept up with the field enough. The reason that graphene would be a good ultracapacitor material is it has an extremely high surface area. Okay?
Right.
That's the key. You want a high surface area for a capacitor, and I imagine there will be some applications there.
Yeah. Got it.
I looked at guitar for ultracapacitor work and can never get it to approach graphene because it's not a single monolayer of atoms. Right. It's just can't match.
Yeah.
So it's with guitars, that's not happening there. Okay.
Yeah. So graphene is just a single layer of atoms of graphite.
Of graphite. Yes.
Does that not mean that if we wanted to test the capabilities of graphene, we could just use graphite, or is there some specific process that makes it more perfect?
There, you'd have to ask a graphene person. You want better crystals, so a lot of people take great pains to grow good quality, high crystallite size graphene. You know, where the crystalline grains are maybe a few millimeters across. Okay, not microns.
Yeah.
So,
yeah. As far as like the, you mentioned the fact that it could be a good ultracapacitor. Is that because there is no room? It's basically in a vacuum, and so there's no room for.
No, not in a vacuum. It's I have to get back to surface area. It's just a high surface area material. Okay.
Okay.
Relative to its mass would be dictated by the weight of the carbon atom.
Right.
Okay, so you expose more carbon atoms to your electrolyte solution than a material like graphite, where some carbon atoms are hidden deep in the bulk of the material. Okay,
Got it.
I hope that's clear, right?
Yeah,
right.
That makes sense.
Okay.
So talk to me about batteries, because I don't really understand how they work.
Well,
here, sorry, if you could pull your microphone.
Pull mine. How do I describe batteries to an undergrad? In a lot of ways, I start out with, usually when I teach a course, sometimes I talk about corrosion first. And so everybody experiences iron.
Right.
It corrodes. That's a spontaneous, rust, a spontaneous reaction. That's because there's a driving force for the electrons in metallic iron to be lost to water, to oxygen in the atmosphere.
Got it. So it's not stable.
It's not stable.
Sense.
So in a battery, it's sort of a controlled process because, an old type of battery like the lead, the lead batteries you see in batteries, the sulfur, sulfuric acid, lead acid batteries. That's a process where you have one form of lead on a negative electrode that's higher in electron energy rather than what's on the positive electrode, which is on the positive electrode, and electrons will flow from lead in a higher energy state to a lead form in a lower energy state. That's the discharge.
So they want to be similarly. Are they all flooding to one side, or is it more like we're trying to even out the plane?
In this case, lead's not moving around.
The electrons.
It's electrons in the circuit.
Yeah.
What's moving around in solution is sulfate.
Got it. Okay.
An ion from the sulfuric acid.
Yeah.
And the lead in a higher electronic state is called the reduced form. In the lead in the lower electronic state is called the oxidized form, and the reduced the electrons will move from the negative electrode into the positive electrode through the external circuit. It's like water flowing downhill.
Got it. Yeah.
Okay. Now to charge it up, you got to pump water uphill.
Right.
Okay. So
and that involves putting more electrons in, or is it the same amount of electrons?
The electrons, you'd have to push the electrons uphill into the depleted negative electrode, the higher energy state.
Okay.
Okay. Because it's been depleted in that case. Okay.
Why is it higher energy if it's depleted?
There's just less of it. It's like water behind a dam. You have a higher state and a lower state, and people imagine water flowing downhill. Now, they'll go back down a little, but they don't go down all the way. You just have to pump water back uphill. Okay.
Right.
Lead acid batteries never completely discharge.
Yes.
Okay. If you do that, it's done for.
Yeah.
Okay? Most batteries are like that.
Okay? Yeah.
So it's just thinking of water behind a dam, and you allow the water to flow out of the dam, and you get an energy out of that, and then you push water back up a hill, and then you charge it up again.
So that it can flow down again.
Yeah.
Right.
Yeah. In this case, electrons are that water.
Yes.
Pushing electrons up. Yeah.
Right.
Okay.
So why is the negative state the one that you store them in as that's when the battery's charged, it's all in the negative state, and then it flows to the positive state?
Okay. Trying to think of a good analogy here. That's the best I can do. Is that you have electrons in a higher energy state behind the dam,
and then it flows
downhill.
Yeah.
Right. Okay.
Got it.
Okay.
So what enables those electrons to go back uphill?
You put work into the system. You charge it up. You push it up with a charger. Okay. You just you just reverse the like the systems you have here. You're putting working electrical energy into the system, and you're putting pushing water back up, or the electrons back uphill.
Could you move your mic just a little?
Oh,
Sorry,
yeah.
you're fine.
Yeah. Oh, yeah. So, yeah, it's like the chargers in your in the battery systems they have here. You're just using electrical work to push electrons back uphill.
Are you making those electrons more energized, and so they naturally move back?
Yeah, in a higher energy state. Yes.
Okay.
Yeah.
So they naturally want to go to that higher energy state.
Well, after you put
Some
work
juice
into
into
the
them.
system.
They're a little lazy.
Yeah, right. They are. They want to go back downhill. Right.
Yeah.
Yeah.
So why is it that if you cut open like a lithium-ion battery,
Mm-hmm.
it suddenly bursts into flames?
It can. Yeah. Have you tried that?
My brother did, actually. He took out the battery from my computer and cut it open and then dropped it on our hardwood floor. So we've got a nice little burn mark in the middle of our kitchen.
Okay. Well, in lithium-ion, there's several failure modes for lithium-ion batteries. One of which, the one I'm familiar with mostly, no, I don't work on lithium-ion batteries, surprisingly. Yeah. So the one I'm familiar with is when the two electrodes touch each other, then you get a short circuit.
Got it.
Now, so there's membranes between the two electrodes to prevent that. But the membranes will they're a resistor now when you put a membrane between the two. So you got the key is for lithium-ion performance to put them as close as possible.
Right.
Okay. And that comes at a cost of possibly, if you have poor manufacturing techniques, of the two electrodes touching each other, and then you get the spontaneous discharge and lots of heat, and you have an organic solvent that likes to burn.
Right.
Okay. So then carbon material burns, and
yeah.
Okay. So in your brother's case, boy, I never tried that. I remember as a kid opening up D cells and nothing ever happened.
Yeah.
Right?
Yeah.
So I'd have to give some thought about what would cause just a lithium-ion battery to burn spontaneously. You just open. I imagine he must have touched the two electrodes together when he did that.
Potentially, I wonder if it was also the metal scissors. Maybe, I don't know.
Well, yeah, the metal scissors, will provide a form of conduction between it. Yeah, so it's essentially be shorting out the two electrodes.
Got it.
Okay. I mean, now I'm really. Some lithium-ion experts going to see this and chime in, but those are just best guesses on my part. Right.
Yeah.
What every kid does
is cut things open, see what happens.
Battery.
Yes.
Lead acid battery or something like I did, or D cell. Yeah.
Yeah. Right. Okay. Couple more questions on graphitic material on your guitar.
Yeah.
Is it possible to make it more perfect by when you're manufacturing it, as it were?
Yeah, if you look at synthetic graphite, they go up to maybe 1,500 degrees Celsius, I believe.
Good night.
Now we're doing this at 900. Yeah. So some engineer that sees this and sees that you're making lousy graphite, and that's essentially what we're doing.
The point.
So yeah, that was the point. And I don't have lucky for me, I don't have a furnace that goes up to 1,500, because we might have just been making graphite by now.
Yes.
Okay. But so I imagine, if you do my process at 1,500 degrees Celsius, you'll make graphite. Now I have a colleague. This is the same colleague. He's still interested in my material. I don't bring up his name because I don't know if his employer wants him.
Totally fine. Yeah.
So, but he took some guitar and slowly heated up to 1,500 degrees Celsius, and he said he saw loss of mass on this material. Now it didn't completely disappear, and he asked me what that loss of mass might be, and I said, I bet it's hydrocarbons coming from guitar. These are these hydrocarbons that give rise to the defects. Okay.
So you're burning off the imperfections.
Yeah, I think you're burning off the imperfections. You now at 1,500 degrees, or I think that's what he's working at. He's making graphite. So he's sending this back to me now to look at it to see if it behaves like graphite, at least with our electrochemistry type of background here.
Got it.
So, okay.
But there wouldn't be really a point to doing that because you can find graphite pretty easily. Is that correct?
Well, commercial graphite's pretty readily available, and crucibles are made out of graphite for metalwork. Yeah, because we discovered the lousy form of graphite is actually better for a lot
of things.
For a lot of things, right?
Yeah,
but it's just been overlooked. Right?
Yeah. So how do you go from vegetable oil to to this guitar substance?
Yeah, I wish I knew. Okay. I published a paper on this, maybe 10 years ago, where we did some what's called Raman spectroscopy, and we'd heat our material up to 300, 400, 500, 700, and we could see changes in the Raman signature characteristics.
Is this ramen noodles?
Same pronunciation.
Yes.
It's a Raman, named after the Indian scientist that worked on
slightly different.
Yeah. So I used to call it Raman, and an Indian student commented it's pronounced ramen, like the noodles.
Yeah.
Right? I
yeah.
said, okay.
I guess it's pronounced ramen.
Right. It's called ramen. But it allowed me to figure out that we were going from hydrocarbons to more carbonized material to even less carbonized material, or hydrocarbon-like material, to guitar in the end. And in the end, what you see out of Raman spectroscopy is it's a very disordered graphite.
Right.
Okay. And so I guess in this field, I would call a trajectory. You can see that trajectory. Now, what's occurring at the every chemist wants to know what's occurring at the atomic level. That's actually can be difficult if you don't have the right tools. There's no tool to see this. Okay? Right now. So we had to visualize in our minds what might be going on. And so it's not a completely satisfactory. Right. Yeah. People have asked me. I've tried to get computational theoretical chemists interested. They're always busy, but can you visualize the what's going on at the atomic planes of guitar, and maybe explain the waviness, the extreme waviness in the structure from the atomic force microscopy of guitar? And I don't know what that structure is.
Yeah,
I don't know.
Fascinating. And I would assume you don't just put vegetable oil in the furnace, right?
No, we spray it in. It's sprayed in through a nozzle.
Got it. But there is carbon in vegetable oil.
Oh,
and you just basically heat it up over the course of several hours. Is it days?
It takes about 45 minutes.
Oh, really? Okay, so not that fast. You basically just heat it up until it naturally becomes this.
Yeah, we know that we've got the process down. So we know it. We do it at a constant 900 degrees Celsius. That it'll form guitar, and we my students have learned to look at the soot coming out of the end of the tube, and it goes from this black to this white smoke, and they know that at that point it's guitar.
It's guitar.
It's sort of like you got the new pope there at the end. Okay. Is it the white smoke?
That's a fantastic analogy. What happens if you just leave it in there, even after the white smoke?
Nothing.
Nothing.
If we're careful about keeping oxygen out of the system, and that's what the nitrogen gas is for, then essentially nothing happens. It'll just happily sit at 900 degrees Celsius.
Got it.
Okay. The question becomes, what happens? You go higher and higher in temperature. We may have that now. We may probably just make graphite.
Right. A purer form.
Right.
Got it. So, and you mentioned you leave it in there, and then I forgot what you said.
We could leave it in there indefinitely at 900, and nothing really happens.
Yeah. Oh, sorry. Why no oxygen? Why?
Because if you have oxygen at high temperature with carbon, you'll make carbon dioxide. Okay.
Got it. Okay. There's our problem. So, and why does it form this guitar as opposed to like coal or some other carbon-based atom?
Or graphite. I don't.
it's probably the activate. There's something always in chemistry called activation barrier. It's just not at a high enough temperature to get over the activation barriers to shake out all the defects.
Got it.
Yeah, and
yeah,
so that's why the guys that make good quality graphite have to go to much higher temperatures. And
right.
I think it's actually over 1500.
Yeah, it's
really
toasty.
It's yeah. Oh yeah.
Yeah. What is the Raman? Is it a process? Is it a substance?
No, it's a type of specific. It's based on a laser energy that causes the electrons and material to go to a higher state, then decay back, and you scatter light in all directions. Okay.
Whoa.
Yeah, and so you look at the scattered light, what's coming off.
Okay, so it's similar to recharging a battery, and then immediately draining it, or
sure. Yeah,
something like that.
Yeah, and just watch the when an electron decays, it'll emit light.
Got it. So it's not like losing energy. It's
well, there's
being
a lot
destroyed.
of energy. Yeah.
But it's unlike a battery. It's actually like the electron is being destroyed. Is that correct?
No, the electron's like a ball that you throw up in the air and it comes back down.
And when it bounces, it creates light.
It creates light when it's falling back down. Okay.
Got it.
Okay. If it goes back down to the same state, that's called Rayleigh scattering. But if it doesn't make it all the way down, that's called Raman scattering.
And why do you look for this Raman scattering?
That scattering is associated with structural, in terms of carbon materials, structural characteristics. Okay.
Got it. So you're doing this process on top of this guitar, so that you can discover if it has all those imperfections.
Yeah, you can. You can see in Raman there's called for carbon there's called a D band and a G band, and some people call it diamond or defects for D band, and the G band for graphite or good. Okay, pick your choice there. But so in good quality graphite, you'll only see the G band.
Right.
Okay. With bad quality graphite like ours, you'll see lots of defect bands.
Got it. You call it diamond? Is there any correlation to actual diamonds?
Yeah, diamond has a different, almost different type of. There could be diamond-like characteristics in guitar, and that would only be that the instead of a chicken wire fence, you have a tetrahedral structure around carbon. Right.
Got it.
Diamond's a completely tetrahedral structure. Okay.
Is guitar stronger than regular graphite?
No, it's weaker. We've tested that.
Okay.
Oh yeah, it's pretty brittle.
Okay. Very brittle.
Yeah.
Got it. So, and why is it that the electrons scatter light as they're descending in this Raman?
Wow. You need to talk to a quantum chemist, basically there. I just take the phenomenology and apply it to my field.
Okay.
Now, that part, that's a good question. Right?
Yeah.
Okay. Right.
Well, I'll have to ask someone else.
Yeah, right. Why does Raman scatter? Why are you looking at a scattering effect? I heard that this isn't true, but every 3-year-old will ask their parents, "Why is the sky blue?" And you can't answer that, right?
Yeah.
There is, until you take a 3rd-year course in chemistry, and physics probably similar, and it's Rayleigh scattering. Blue light's scattered more efficiently than red light. So the blue haze you see is from the scattering. So that's somewhat related to Raman, but Raman is a slightly different effect. Okay.
Yeah, now I have questions about why the sky is blue.
Okay, right.
The scattering of light, what's it scattering off of? Is it just the particles in the air?
Yeah. Mm-hmm.
Got it. Okay. And they reflect blue light better.
Yes, they scatter it better.
So, and then the reason that, like, if we were to go to Mars, potentially the sky would look a little more red because there would be different elements in the air that would scatter it differently?
That's a good question. What does the Martian sky look like? I
don't
know. A lot of red on Mars is just basically the iron.
The iron, yeah.
You see in the deserts around on Earth too.
Yeah.
So, yeah.
There you go. Well, we'll kind of wrap up here. I always like to ask, what's your best piece of advice you would give to anyone watching?
Stay curious.
Yeah.
Right. I think
And, you know, you have to maintain a certain curiosity along with that, as a little bit of drive and determination, right?
Right.
Okay.
There you go.
Yeah.
Where can people find you, all of this work and guitar and all of that?
I guess you could look up my website, although you know, for the layman, they might get tired of it pretty quickly. Okay. Anybody that's into carbon materials might be interested.
Yeah.
Yeah.
There you go.
Okay.
Thank you so much for coming on the show. This has been fantastic.
Yeah.
Really
Yeah,
appreciate
you're
it.
welcome.
See you guys.